Function transformations. But before we could talk really about function transformations, I'd first have to introduce you to the parent function. So let's meet the parent functions, these nice parents here. And this handout is in the module. You should be able to get a PDF of it from the Canvas page. But the parent functions are kind of, you could think of as just like a base function without any kind of shifting or transformation occurring. So you see we have a straight line, a linear line, we have the absolute value, quadratic, square root, cubic, cube root, exponential, logarithm, the rational inverse, inverse squared, greatest integer, and constant function. And just by going in Google and typing in parent function handout, you could find some that might have some different ones. Another good example are when you get into trigonometry, if you've gotten into trigonometry yet, your trig functions have kind of their parent function and then their transformations, as well as your conic sections. So we have a parabola here with the quadratic, but we also could have a circle, an ellipse, and hyperbolas that also have parent functions. So let's look at one example and kind of use that to kind of set our frame up for learning more about how to use transformations to graph functions. So I'm going to turn your attention to the other handout that should be contained within this module or somewhere on the Canvas page, which is graphing using transformations. And what really is going to be at the heart of it is that you're going to use one of your parent functions as kind of the base. And then you're going to apply a transformation to that parent function, to its graph or to a collection of points to graph the now transformation. And so there are several different types of transformations that we'll deal with. There's horizontal shifts, horizontal stretches, circumpressions, reflections about the y-axis, vertical stretches and compressions, and we're going to look at each one very quickly here, and in the how-tos you'll learn a little bit more about it. Let's look at the parent function for the absolute value function. Y is equal to the absolute value of x, and this is the parent function, and notice we have this point right here, 0, 0, that we'll kind of use, and maybe we'll look at two of these points just to kind of identify where we're at. And this one is 1, 1, and we're going to first try to talk about what a horizontal shift is and how that applies. So let's kind of think of this function as really f of x is equal to the absolute value of x, and for the horizontal shift to occur, what we say is that we're going to find f of x, let's try minus 1 just to keep it simple, which means then we would have x minus 1 in here. And what this is saying is that if we have a minus c, then the graph shifts right c units. So what we can expect from our points, for example, the point 0, 0, we're saying that the x, 0, should be plus 1, and then that the y should stay the same. And then we should end up having a graph that looks like this. And so we see that the point that was at 0, 0 then got shifted to 1, 0, which is exactly what we expected from our definition of what that transformation should do. We also saw that 1, 1 also got shifted over, and we increased the x-coordinate by 1. And so everything kind of got just shifted over to the right, and that's a horizontal shift. Now let's talk about a horizontal stretch or compression using again the absolute value function. Let's go ahead and look at something like this. Putting it into my function, this is what we have now. And let's identify a couple of these points again to kind of watch how they change. And this one is at negative 1, 1. Here we have this case of b here where c, absolute value of c, is greater than 1, since our c is 2 in this case. So we should think that there should be some sort of horizontal compression by a factor of 1 over 2 in our case. And in both cases we see that this is what ends up happening to our points, right? So again, if we're kind of seeing what happens to these points, 0, 0 should be 0 over 2, 0, but notice that actually it's just 0, 0. So we don't expect any kind of movement because we don't have a shift, right? We don't have that horizontal shift we did a second ago. But we have the points 1, 1, negative 1, 1, we see that they will get transformed to these points. And we'll see if that actually pans out, because the graph looks like this. And we see that sure enough, 0, 0 stands in the same spot. And now if this is 1 and this is negative 1, we see that the points that we had, 1, 1 and negative 1, 1, have now both kind of compressed in, right? So our graph kind of got shrunken in at each of these points, and that's why we have a horizontal compression. Horizontal means like kind of left and right, vertical is up and down, so going left and right we got pushed in, right? And that's why we call it a compression. Now let's do a quick reflection about the y-axis. So it just says that if we input in a negative x for our x, we have this, and all it says is that this is what should happen to the points, right? So if we take a point like 0, 0, it should be negative 0, 0, but really that's the same thing as 0, 0. So again, we're not shifting our 0, 0, our little vertex around. We're just hoping that it's going to reflect it about our y-axis right here. So let's see what it does to our other points. So again, we could take points such as, you know, negative 1, 1, and see what actually happens to them. So 1, 1 should be now negative 1, 1, and negative 1, 1 should now be positive 1, 1. Notice they're just kind of changing which points are which. So if we're thinking about it, this point supposedly going there, and this point supposedly going there, we are symmetric. So looking at the graph, we see that everything stayed the same. That's because the points that were on the right-hand side of the y-axis got flipped to the left-hand side, but the points on the left-hand side got flipped to the right-hand side. So it just kind of flipped over, and it looks identical. Now looking at a vertical stretch or compression, we've already done a horizontal stretch compression. We did a quick example of compression. Let's look at a vertical one. So according to what it says here is that we should be multiplying our function by something. Let's do something pretty similar to that last one. So this will be 2 times our function, which is absolute value of x. And we picked a c that was greater than 1, so we're doing case A here. So it should be a vertical stretch by a factor of 2. And it says in both cases that this is what should happen to our points. So again, picking some of these main points here, we expect 0, 0 to become, which is the same thing as 0, 0. So again, we're not shifting. And so that's going to be our prediction, and our graph looks like this. And we could already see that it looks skinnier, right? Which we could have thought as a horizontal compression, or we could think of the fact that it looks taller now, which is what we mean by a vertical stretch, right? And again, our prediction for the point 0, 0 is that it stays in the exact same spot, and we were at the point 1, 1 and negative 1, 1, and we see that those points in D became 1, 2, right? It got moved up like this, and negative 1, 2. All of the points that we have on this graph have kind of been stretched up. Now let's do a reflection about the x-axis. So we did one about the y-axis last time, which actually didn't change our graph at all because of the way that our graph is, but now we're going to go about the x-axis, so this horizontal axis here. So we're kind of imagining things should sort of get flipped around here, right? But let's see what happens. So according to the handout, this is what we'll do it by just making a negative version of our function. So that would look something like this. And this is what will happen to our points, right? And so if I have the point 0, 0, which I have already marked these points here, I expect to have a 0, negative 0, but that is just 0, 0, which is expected, right? It says this point, as things get flipped, it'll just stay in the same spot. We have 1, 1. We expect that to become 0. Oops. We expect that to become 1, negative 1, and then we have negative 1, 1, which we expect to become negative 1, negative 1. And let's take a look at the graph. Cool, and it looks to be about right. Things got flipped over. Looking at our points, 0, 0 stays in the same spot. We were at negative 1, 1 and 1, 1. And we saw that the point 1, 1 should have become 1, negative 1. And the point negative 1, 1 should have become negative 1, negative 1, and in fact they did. So we see it just got reflected across that horizontal x-axis. Lastly, let's talk about vertical shifts. So we did a horizontal shift, meaning left and right earlier, and vertical shifts are up and down. And so we expect to see something with our graph to move up and down versus earlier where I think we moved it to the right one space. So let's take a look at what our handout says we need to do the function for that to happen. And let's just go ahead and do a +1, see what happens. So we take our function and we're going to add 1 to it. According to our handout, since we're adding a plus c, we're looking at case A here, this should shift us up c units. So in our case, it should shift us up 2 units. Since I decided just the +1 here, we're just going to shift up by 1 unit. And let's see what that does to our points. The point 0, 0 then, we expect to go to 1, we expect to go to 1, 2. Point negative 1, 1, we expect to go to negative 1, 2. So let's look at the graph and see if that's true. And this looks about right, because if we look at the parent, we're down here at 0, 0, and it looks like its child has now been shifted up 1 unit. So at the point 0, 0, we expected that to become 0, 1, which is exactly what it did. We also had the point 1, 1 and the point negative 1, 1, and getting shifted up 1 unit, we stay at 1 for our x and the y becomes a 2. Same thing with this one. We shifted up 1 unit, the x is still stayed the same, and the y is now at a 2. So we have a vertical shift up. Lastly, I just wanted to briefly mention something called standard form. And roughly it looks something like this. And it just has sort of the different shifts, like this horizontal shift will be h and the vertical shift would be k. And we have some sort of our compressions and stretches right here with a in terms of it getting kind of moved in and out. And to kind of give you a sense of what it really means is we were looking at the function absolute value of x. Often we're going to see that just written like this when we're talking about standard form. And so you could already look and say like, oh, what is h and k and what is a? And if we're looking at the original function, right, it looks something like this. And we have kind of a central point right here, which is 0, 0. And what it really means is that h is 0, k is 0, a is 1. And that gives us f of x is equal to 1 times the absolute value of x minus 0 plus 0. If you simplify this, we just get absolute value of x. Kind of looking at something a little bit different, we graphed earlier something that looked like this. And we just shifted it, alright, to the right 1 spot. Let's play with that a little bit more. Let's shift it to the right once and up twice and see what that would do to the graph. Comparing it to this standard form, we see that h should be 1, k should be 2, and a should be 1. And if we plug that back in, we would get this. And what does that mean? Well, it means that we took our 0, 0, we shifted that over 1 spot, and then we went up 1, 2 spots, because this was our h spaces and k spaces up. And notice it's h and k is the same thing as 1, 2. And all the points would kind of follow suit just like that. And so I just kind of want to get you used to this form where it's kind of written so you see how the points are moving, and that's kind of usually signified by the h and the k. It's kind of either a vertex or a main point, and it's kind of built into the equation on how that's moving up and down. For example, if you had the function f of x equals x squared as the parent, we could say in standard form all of these should be written in some form such as this, where you kind of see those shifts and those compressions. Same thing can be done for even, say, the square root of x. In standard form, this will all often be written as the x minus h in the square root and plus the k. And so that will have some sort of points that'll be shifted h and k, and stretched or compressed by a factor of a, or 1 over a.